All right. Second video of the series. I try to improve the audio now. Yesterday I've been working on audio, setting up mach-sysaudio and mach-opus from Match. And I am having a problem with sounds being concatenated, and that's weird. But I'll show you what I did. So the pipeline to compress audios looks something like this. Let me show you. So there is a make file that converts all the audios in the sounds folder to a raw opus folder, directory containing .opus files for each of those input files. And it's using FFmpeg with libopus to convert it, making sure that it uses 2 channels, and the bitrate is this shouldn't be necessary because Opus by default uses that bitrate. After all that conversion passes, what I do is to use protocol buffers with a sounds database root structure to create a sounds.bin file, which is 4.1 megabytes for almost 300 sounds, WAP sounds. That's pretty good, but it takes a little while to load. I'll tell you how I did it. So in my structure, my file structure, I have a folder in the client called here it is. In the client called systems, and inside systems I follow this same I call it life cycle hooks because I am an old school React developer. Life cycle hooks with a couple functions, init, start, the init, and update. And then I have a couple of shared helpers, system managers, which use the beautiful meta programming of comp time of SIG to iterate a collection of systems and either init, the init, call the update or render functions, and of course the start function if it exists. And in case you don't know SIG and this is the first time you are encountering this syntax, this inline for is unwinded in compile time. So this part here, the argument for the for should be static, known at compile time. That's my understanding of how it works. And you can do very interesting things like, okay, in this case, we don't know the type of the systems. So we assume, otherwise it will fail, that it is a struct that contains fields. So far, so good. So we have a list of fields that we are iterating one after the other, and this doesn't get compiled into an actual for. It's one statement after the other. And from the systems, we get the field that we are trying to use. Since this is a const and this entire sentence is comp time, the system is like actually doing writing this code, system.abc. And we can use it statically and know if it has a declaration called start, and only then call the system.start. This kind of helpers have improved. Very useful for me. I'll show you how it works. So in the main file of the client, I have a list of systems. That's simply importing the file, and using the lifecycle hooks, I could use the root level of the file to put the functions in it, the init, and etc. But the lifecycle hooks are somehow very organized, because inside this struct I can put all the functions that I know for sure that should exist, and then leave public and other functions at root level that can be used from another parts of the client. So first of all, we start the ECS engine. This creates the registry, and we store it in that global context. And of course, it needs it. We start the engine itself. This starts match, and after that, the sound. And in the sound, we're using sysaudio from match and mach-opus to decode. And all of the sounds of this game are indexed using integers. So we're going to store them in an auto hash map of U32, and they're directly the decoded opus files. Start the context, start the device and the player. And then I'll create a sound group for the ECS. Every component, every entity that has a playing sound component will be able to emit sounds. And this is the sound index, the same that we use in the resource. The index of the sample that we are playing, the volume in float, and the amount of loops that are remaining. Once this hits 0 and only 0, the sound stops. If this starts being negative, it will play forever in a loop, and if it contains a number greater than 1, eventually it will reach 0 and stop. And after that, we have a delete entity upon finish flag to do exactly that. Okay, so how does this look? I am not sure that the sounds are going to be recorded. In any case, there are some insects chirping. So the sounds are being loaded asynchronously in a different thread. And as you can see, it takes a while to load all the sounds. If we were using a WAV file, this should be much faster, but takes much more disk space, which is an interesting trade-off. I think I'm going to go in that direction, because it's like 15 seconds to start it. It's simply too much. And again, I don't know if you can hear it, but 4 sounds were played in that click, and that's not good. And the code that plays the sound is relatively straightforward. There is one huge pending optimization here. How it works is that you create, I believe it is the player. Yeah, so you create a player and you provide a function pointer to the right callback. And this will be expecting that you write n amount of frames to be sent directly to the sound driver and later on to the speakers or whatever is playing the sounds. So each sample is one point in the curve of the actual wave of sound. For me, that I come from the JavaScript world, I'm surprised that computers are this fast, but I think that's how things work. And another super important thing is that this runs in the exclusive thread for the sound itself. And based on the name of the thread, I think that is controlled by the operative system, at least in Mac. Okay, so we iterate over the desired frames, and then we iterate over the entities that have a playing sound component. We get the sound using the ID, I think that plain arrays would be better to get this sound ID, given the fact that the sound IDs are 300. We could pack all of them in one contiguous array of memory, vector of memory. Once we get the sound, if it exists, if it's loaded, the sound has a predefined amount of channels, stereo, mono, 5, 6, or whatever number. And if it is greater than 2, we only take the first two samples and store them into our temporary sample. And otherwise we use just one. And I think that this code makes more sense for left and right channels. And after that, we increment the index of the sample that we are reading by the amount of channels. This is super important. The samples are stored sequentially for each channel. So if we have 4 channels, we will have the channel 1, 2, 3, 4, and that's one sample, and then 1, 2, 3, 4, and that's another sample. And since we are playing with sound waves, I think that the naive approach that just works is to add all the samples together. So if you're playing a couple of sounds, you simply add them and it will work. A huge optimization to do here is to actually change the order. Instead of creating one frame and then for that specific float that we are trying to get, iterate for all the sounds, we should create something like frames, slice, frames, F32, blah blah blah, and then populate all the frames at once for all the sounds, because that in theory should optimize the caching of the CPU, trying to actually read the memory for the samples and preventing cache misses and things. But to start, this is okay. So what I'm going to do now is to try to debug this, creating a UI to actually see how the sounds are behaving. And to do so, I'm going to use the render function over here. And I'm going to import CUI. I think I have some code to copy and paste. That will be easier. Scrolling buffer. I'll need these two. Okay, I'll just copy everything. Okay, so the scrolling buffer is a data structure that I will reuse from the profiler. And I'm going to use it to generate a graph of the sound that is being played. And that is so to see if the 4 sounds that are playing concurrently are actually the same sampler, the same samples, or it is somehow corrupting the memory and reading the next couple sounds. History seconds. We are going to call this sample. we are going to store around, I don't know. Okay, and then begin plot sound wave. This is going to be time, and this is going to be wave. This is the type. I better create a different file for this. So this is going to be the X and Y axis. And then now is the sample number. Okay. I better create some life cycles hooks for this. Sound wave time wave. This should be the volume or something like that. T is the current frame. This is going to grow very rapidly, but we don't care about that right now. And we need another function. Wave point. If the debugger is active, we're going to add a point. Oh, values one per channel. Value right. And we are going to increase the current frame by 1. That should be an int, but the plotter requires floats. Use it now. Current frame. Left channel. Now we call a waypoint from here. This is not good for performance, but it is just a debugger. Last thing is to see where the system UI is being used. Render scene maybe? Developer UI, that makes sense. Will it blend it? Oh. Nice. Okay, developer, debug audio. It is not moving. Ah. Amazing. That was so cool. Okay. So all the sounds are being recorded. Those are 1, 2, 3 sounds. Okay. We are going to use the ancient technique of placing breakpoints. The sound system. We are going to stop right after the first sound stops. Okay, so the entire thing, this is one click sound and this is another sound. The entire thing is one huge blob of bytes in the shape of one sound. I already checked that the opus file itself is not corrupted, it's just one sound, but I don't know why this is concatenating several sounds together. I want to check something out. Amazing. The sounds loading thread. The goat stream. Sound opus get slice. The sound itself is not corrupted, but maybe, just maybe, the protobuf library is. So this is the sound number 4. that's interesting. Power of 2. Length exactly the same as the number 3. What is this length again? 1, 2, 3, There is one tool from protocol buffers that is used to debug. That can print out the contents in the terminal. Protoscope. That was a very long shot. I forgot the mounting point. Okay, what I want to do, docker exec docker run is to mount the local directory. There we go. Firewall. Protoscope. And this not. I better. Yes, that's it. Okay, what I want to do now is to check whether the protocol buffer is corrupted or no. And I look for the number 4. Side by side with the number 3. It doesn't look the same file in the protocol buffer. So I assume the well-known and tested JavaScript library works, and the version that we had to tweak for this is not working. Okay, how do I ensure that? Audio debugger sound. Where's the locators? Arena allocator. Hmm. Yeah, the memory seems somehow corrupted. Okay. Seems like the protocol buffer is reading the same file for the entries 3 and 4, potentially others. Although with different rates. This may be another issue. Which one is it reading? Okay, so 3 and 4 are both the same 3. Which is all right. I need to jump, but I think that I have a cue where this is maybe in the protocol buffer reader.